Hi, everyone. Happy Thursday. Welcome. I'm super pleased to introduce my colleague here at the Joint Institute, Marshall Wise. Marshall has spent decades and decades at PNNL and has really seen over the course of that time a lot of the developments of GCAM, and he's worked a lot on economic and multi-sectoral modeling of regional and global energy and agricultural systems. He's one of the core developers of GCAM and its predecessors, and he has a lot of expertise in areas including the electric sector, agriculture, land use, bioenergy, and international trade. And since January 2022, he has been the PI of GCIMS, the flagship SFA program of DOE's multi-sector dynamics program. Welcome, Marshall.
Thank you, Ben. One of the flagships. There's a lot of great programs there. Yeah, it's been mentioned. I'm Marshall Wise from PNNL. I'm in College Park at our office there, along with Ben and some other people you may know. So it's just my privilege to present on behalf of our team, the GCIMS and the GCAM modeling teams, an overview of the GCIMS project. And today I'm going to spend a bit more time on the GCAM model, the Global Change Analysis Model, is one model in the GCIMS, the Global Change Intersectoral Modeling System project. So just get that naming out of the way. So the GCIMS project, funded by the Multi-Sector Dynamics Program of DOE under EESM. So our vision and our framing goal has been to improve the understanding of the complex interactions among sectors that are key for understanding the evolution of the integrated human Earth system. So this research involves studying energy, land, water, critical materials, other important related systems. We do this analysis at regional to global scales. We do this with an emphasis on building and maintaining an internally consistent open source modeling framework, which is the GCIMS, or the Global Change Intersectoral Modeling System. So our project has a deep multidisciplinary team, including physical scientists, computational scientists, engineers, economists, from very senior staff like Ben to recognize experts in their field, also kind of like Ben, and from postdocs to students, people of all levels of experience. At the bottom of this chart, you'll see some of the breadth of the project team. And it's not just P&L, we're strengthened by having GCIMS team members at several other national laboratories and several universities, as well as a member or two who also work on the E3SM team. So I'll quickly talk about some of our current focus areas for the project. These areas reflect further work based on capabilities we've been developing over the last several years, and some newer areas which we're well set up for with our multi-sector modeling approach. The first area is energy. Energy has long been a foundation of our work. Using our multi-sector dynamic analysis approach, our goal here is to analyze potential scales, roles, and impacts of energy resources, technologies, and applications, and we do this in the domestic and global economic context of energy production, transformation, demand, trade, and security. The secondary, which is becoming a lot more relevant, has always been relevant, it's getting a lot more interest, is the critical minerals and materials. So we're using our multi-sector modeling to quantify, explore demands, resource supply chains, domestic and global markets for critical minerals and materials, things that are linked to the energy sector and the computational needs of an evolving economy. The third area is based on expanding our advanced computational methods, and I'll mention two angles on that. One is that we're developing novel computational techniques for AI-assisted facile model integration. And a second area is we're developing machine learning approaches for exploring large ensembles of scenarios, quantifying the impact of uncertain drivers. And a more recent focus for us is analyzing data centers, large-scale data centers, and AI. So we see data centers as a key use case for our kind of work, as it brings in many areas of research and analysis that we incorporate. So we're looking at the growth of future growth of data centers, quantifying the requirements for electricity, water, capital, and critical materials. And then also a broader goal is to look at the potential impacts both from and on technological and economic change. Of what kind of impact in the long run would the AI developments have on the future economy and the demands for energy as part of that. So we gave presentations on these areas at our GCAM annual meeting last month. And I think afterwards I'll find a link to the presentations there and send it on, so you can see that. So now I'm going to get into the global change analysis model itself, the GCAM model, which is I'll show you where this fits in with our family of models. But the GCAM is a multi-sector, multi-regional dynamic model focusing on energy, agriculture, water, and critical materials and international trade. GCAM economically and physically links long-term, typically run to the year 2100, production and demand in these areas. I think one way to think about GCAM is it is an economics model that has lots of physical detail. So GCAM includes technology, detail, and energy production, energy transformation, and final demand sectors. And in terms of physical detail, we represent energy technologies such as power plants, like electric power plants, passenger vehicles, trucks, trains, in engineering terms. And in the agriculture system, we represent physical representation of crop management practices. We make explicit economic and physical representations of irrigated and rain-fed demand for. And then we look to the right, we see the regional resolution, and we choose this resolution to detail as a balance between tractability and usefulness for whatever questions we're looking at. So we currently divide the energy and economic system. Countries are aggregated into 32 regions. We model 235 water basins around the globe. The intersection of this results in 384 land use regions based on that combination. And also, I'll mention we do have a version called GCAM USA, where we have 50-state resolution for the energy system within the global context. So looking at GCAM in the GCIMS context. So GCAM and the other GCIMS models are open tools and designed to operate modularly, either as standalone or integrated with other parts of the GCIMS systems. And also there are more tools than there are shown here. We did have presentations and training on many of these tools at our GCAM annual meeting. So GCAM acts as a central integrating model for the GCIMS system, the models and tools. GCIMS is where most of the multi-sector analysis and economics takes place. Not all, but most. I'll just touch briefly here. On the bottom left, you see some physical system models. So there's a Hector reduced complexity Earth systems model. And we also have Xanthos, a bottom-up global hydrology model. And top left we have tools that take raw data and process them and aggregate them to create GCAM inputs. On the top right, we have other tools. You may have heard of Demeter and Tethys, and they go the other direction. They spatially disaggregate GCAM results for land and water use to higher resolution than we have inside GCAM. And then the bottom right, we have Stitches as an emulator that links in detail from more detailed Earth system models in an efficient manner that allows us to run multiple scenarios with feedbacks from the Earth systems to human activity. I won't spend much time on this. So this is from Alan Di Vittorio's recent paper. So you know that GCAM serves as a human system model in E3SM, and there's coupling of land use, economic land use decisions that are made in GCAM are passed to E3SM, but also the fossil fuel sector fossil fuel energy system CO2 emissions are passed to E3SM, and then GCAM in turn makes economic land use decisions using productivity that's returned from E3SM. So that's something that thanks to people like Alan and Ben and Eva, good progress has been made in that area. So GCAM is an open source community model. It's been built and maintained by PNNL. We have used it for analysis for the U.S. DOE, obviously, several offices in DOE, other U.S. administration, and in the private energy industry. Published probably hundreds of papers in scientific journals over the year using GCAM. There's an international user base. We hold an annual users meeting. Lately, it's been in June. Since the pandemic, we've been having that meeting virtually. I think we've had some success with that model. And the DOE's Office of Science MSD program is the largest current and the largest historical funder of GCAM development. So I want to point to GCAM USA, which we are increasingly using in the GCIMS project to address some of the research questions of interest. I mean, higher regional resolution is a good goal, all else equal, but we still see the importance of maintaining the larger context of both the U.S. as a whole, but also the global perspective as a whole, because there are important feedbacks. So GCAM USA represents energy system at the 50-state level of detail, but like I said, it doesn't operate as a standalone model, but it's within the global GCAM model. Because it's in the global GCAM model, state level energy systems both affect and respond to conditions in the domestic U.S. and the global energy systems. And importantly, scenarios of state level energy are physically and economically consistent with the U.S. and global energy sectors. And then I'll finish here with GCIMS and GCAM can contribute to digital test beds, because we can have flexible heterogeneous regional scales for modeling while capturing feedbacks to and from the U.S. and the global regions. Now, a few notes about the solution approach, which I believe is relevant not just for working with the model, but also helpful for interpreting model results. So looking at the figure on the left, GCAM starts with influences and drivers such as population, economics, resources, and technologies. And from this solves a system to compute outcomes. So in the middle is a solution process for GCAM. So GCAM operates by solving each period by setting finding the set of prices so that all modeled markets are clear. The prices of energy, the price of agriculture, the prices of water, the prices of different critical materials. So the system is solved, the system of nonlinear equations, by finding the set of prices so that all supplies, or each supply equals each demand, which results in economic equilibrium, which can be interpreted as the physical quantities of all sectors are balanced and allocated economically efficiently. Prices you can think of as the signals by which multiple sectors communicate to each other. They communicate scarcity and demands and dynamically respond to each other. And then just a final note, compared to some other models that have a similar scope, we call ourselves a recursive dynamic model rather than an intertemporal model, an intertemporally optimal approach, meaning we solve each period independently of future periods. We have expectations of future periods, but we don't have future knowledge or perfect knowledge of future periods as part of our solution. Okay. And I want to mention about our logic choice mechanism for economic decisions. So in general, GCAM resources, production functions, supplies and demands and markets are nonlinear, which results in some desired properties, including increasing marginal costs. You do more of something, it tends to get more expensive. The converse of that is you get diminishing returns to scale. You do more of something, you get less out of it. Because of this, linear constraints aren't needed to bound the solution. The derivatives increasing costs, decreasing returns, allow us to find an equilibrium solution without constraining things. So we make extensive use of the Logit equations and model of economic choice. Logit approach assumes there's an inherent distribution of realized costs and profits due to heterogeneous conditions. And specifically, the market share is based on the probability that a technology has the least cost. Again, this results in nonlinear technology competition. There's a continuum. It also allows historical calibration, which influences future competition. And it also allows us to translate our competition into elasticity terms that some other modeling structures use. Okay, a quick overview of the energy system. What's in there? So this within each region, we have a technology detailed representation of flows through the energy system from resources on the left to final demands on the right. Production occurs from regional resource bases, except for bioenergy, which comes from the agriculture and forestry sectors. Based on economic competition, resources flow to energy transformation sectors in the middle, such as electricity or final fuels. And at the far right, energy is demanded by consumers and industry for transportation, for building services, industrial heat and steam, et cetera. And in terms of structural detail that there isn't time to show here, the transportation is represented by several modes and passenger and freight. There's several commercial and residential services and buildings modeled, as well as energy demands in several industries. And now, a bit about the land use region. So as I mentioned, there are 384 land use regions in GCAM based on modeling the intersection of our energy economy regions and our water basins. So water basins is an important physical regional definition for us because we do not typically, maybe never in our modeling, trade water. Water is something that it's basin, and you trade agriculture, you trade energy, and the water within a basin in different scenarios does affect the trade in those things. Okay, so within each of the 384 land use regions, we represent all land use and land cover, including commercial land uses, but also non-commercial natural lands, and they're represented in GCAM, starting calibrated to a historical base year, and economics drives future changes in cropland. Cropland expansion or contraction at the expense of forest or pasture, change in the mix of crops grown in each region. All this is driven by economics in the future periods. Okay, so in terms of agriculture supply and demand, GCAM has approximately 13 or so crops that we model. We also model different animal categories as food, bioenergy, as well as we model forestry and wood products. We model production in all land use at a 384 land use region that I mentioned. Demand and markets are at the 32 region level. So, for example, the U.S. has about 20 different land use regions or so, but by default, the U.S. will have one market for the crops. And then we account for both food and non-food demand, including animal feed. Demand for a given commodity changes over time in response to income, its price, and the price of substitutes. And demand for food, feed, and energy uses of crops are price responsive. Okay. So a couple of words about international trade in GCAM. So the trade and regional teleconnections are key to understanding the dynamic impacts of scenarios, both globally in the U.S. It's critical to several research areas. Of course, trade and energy and important minerals, having differential regional energy and food prices and access to food is a key scenario result, and also looking at regional resilience and impacts. The ease or difficulty of trade is going to have a big influence on those outcomes. So over the last several years, we developed a capability here so that we consider the GCAM has trade capabilities on par with prominent trade models. And we can parameterize the full range from simple global trade, detailed bilateral trade, or regional trading blocks, or to having no trade. And we do this in energy, crops, critical materials, other things that we modeled. I'm going to finish here with a little bit of philosophy, and then there's a couple bonus slides that I'll leave with. This may seem obvious, but it's not. When in my study of economic models and people's understanding of them over the decades, this is not always true. I mean, we want the results in our model to be a function of scenario input assumptions. So we want flexible data-driven modeling so that input assumptions and parameters are just open and understood to users and can generate very different scenario results. For example, if you give it very different assumptions about costs and resources for energy sources like renewable, fossil, and nuclear power, you want to be able to have the model generate very different scenarios of the future energy mix. You don't want the model to put limits on things and have hard-coded constraints or things that are kind of judgment about saying, oh, well, that wouldn't happen or we'd never do that. And also in terms of agriculture, given very different projections of regional crop yields, you'll get very different scenarios. And we want to be able to use the model to span the possibilities to show the logical outcome of those scenarios. I think I've mentioned that. I will jump into a couple of quick bonus, and I'll finish in a minute, Mark. So a couple of the areas that we're working on that I mentioned earlier. So the critical minerals and materials modeling. So on the right, we build it up in GCAM based on our detail in the energy sector. So the electric power and the transportation, buildings and other demands for different critical materials in the future, the economics of that, the options for using more or less of them and different technologies based on the prices of them. And then on the left, we have the supply that we're building up from the different regions. And then in the middle is the interesting, the complicated stuff of trade. Depending on trade ease or difficulty or assumptions, there are a lot of different scenarios and implications from assumptions about trade in these things. A lot of interesting, difficult questions, but we have the apparatus set up in GCAM to be able to address those questions. I'll finish with this. The other area of new focus is the data centers, which again we want to consider the electricity requirements, the water requirements for cooling, critical materials requirements, but also have some feedback to the economy. How do the services from data centers, how might they affect economic growth? And I will stop there.